After we finish chapter 13, then there's a homework. So you no. The second homework include the chapter 12 and 13 together. I think so.
I just wanted to make sure though, because like we finished it last Thursday, and I wanted to.
Yeah, I think the second homework include both of them, both chapters.
Good news for me.
All right. Okay. Let's continue studying balanced reaction equation. So this time we have an ethanol C2H5OH. It's going to be burned with air. So C2H5OH is going to react with air. That means oxygen and nitrogen. So what's going to happen? So according to the dry molar analysis, 3.16% is carbon dioxide, 16.6% is carbon monoxide, 80.24% is nitrogen. And we are going to determine the balanced chemical reaction, balanced reaction equation. They're the same thing. So we have carbon dioxide, and we have carbon monoxide, and we have nitrogen. And this dry product analysis cannot measure the amount of water, so that's what we need to determine from here. So there's a water. So to solve this one, we assume that there are 100 moles of carbon dioxide, carbon monoxide, and nitrogen in the product. So 3.16 moles and 3.16% of 100 moles is going to be 3.16. These are 3.16 and 16.6 and 80.24. Then we need to determine the number of moles of this ethanol, oxygen, nitrogen, and carbon dioxide. So first, the ratio between oxygen and nitrogen in air is 1 to 3.76. So 1 kilomole of oxygen, there are 3.76 kilomoles of nitrogen. And we need to determine how many moles of ethanol, how many moles of air, and water. So we can check the number of carbons first. So we have 16.6 carbon here. So let's talk about carbon. So we have this one, 16.6 of carbon plus. Here in this carbon dioxide, we have 3.16 moles of carbon dioxide. That means how many carbons do we have? Again, 3.16. So altogether, it's going to be 19.76 carbons. Then how many ethanol we can make if you have 19.76 of carbons? Since one molecule of ethanol has 2 carbon atoms, so that means this one divided by 2, 9.88. So we have 9.88 moles of ethanol in this balanced reaction equation. Then what about hydrogen? We have 9.88. And how many hydrogen atoms in one molecule of ethanol? So let's talk about hydrogen. There are 6 hydrogen atoms in 1 molecule of ethanol, so 9.88 times 6. So these many hydrogen atoms in the reactant. So should be the same as, and each molecule of water has 2 hydrogen atoms. So 2 times the number of moles of water. So what's going to be here? 29.64. So this one is 29.64. So that goes in here. 29.64. So the last one is oxygen. We have, so let's talk about oxygen. So we have 1 oxygen atom in 1 molecule of ethanol. So that means 9.88 times oxygen. So 9.88 times oxygen plus how many moles of air? We don't know. And each has 2 oxygen, right? It's going to be 3.16 times 2. 3.16 times 2 oxygen. So this all means oxygen, okay? You can just get rid of them. That's okay. Plus 16.6 oxygen times 1 plus 29.64 oxygen then you can determine how many moles of oxygen is required. So if you do the calculation, this is going to be 21.34. So this one goes in here, 21.34. So that's how you determine this balanced reaction equation. Once you determine this balanced reaction equation, this balanced reaction equation is for 9.88 kilomoles of ethanol. So you need to divide by 9.88, 9.88, 9.88, everything 9.88. Then we can determine the balanced reaction equation for 1 mole of ethanol. So that is C2H5OH plus 2.16 oxygen plus 3.76 nitrogen is going to be 0.32 carbon dioxide plus 1.68 carbon monoxide plus 8.12 nitrogen plus 3 water. So that's how we determine the balanced reaction equation. So any question about how to determine balanced reaction equation? If you're not 100% happy, then I have one more problem we can solve together to practice how to determine the balanced reaction equation. So we have a propane this time. Propane is C3. There are 3 carbon atoms and 8 hydrogen atoms per 1 molecule of propane. And we are going to determine 3 balanced reaction equations. The first one, when we have the theoretical amount of air. That means 100% theoretical amount of air. Then we are going to determine the balanced reaction equation with 20% more air. And then the last one is only 90% of the propane is consumed in the reaction. So we are going to determine 3 balanced reaction equations. Okay. So the first one, propane. So we have C3H8. So this time we are going to use 100% theoretical air. So air is oxygen and nitrogen. The ratio between oxygen and nitrogen is going to be 1 to 3.76 nitrogen. We do not know how many moles of air are there. And if it is complete combustion, that means carbon becomes carbon dioxide, not carbon monoxide. So after the reaction, this carbon becomes carbon dioxide, this hydrogen becomes water, and oxygen. All the oxygen is going to be consumed because it's 100% theoretical air. So we only have nitrogen left over. Looks like the simplest case, the simplest balanced reaction equation. So let's complete this balanced reaction equation. We can check the number of carbons first. So we have 3 carbon atoms in 1 molecule of propane. So there are 3 of them. And each molecule of carbon dioxide has only 1 carbon atoms. So each mole of propane, we can create 3 moles of carbon dioxide. So 3. What about hydrogen? We have 8 hydrogen atoms per molecule of propane. And each molecule of water has 2 hydrogen atoms. So 8 divided by 2. So how many molecules of water we can create from 1 molecule of propane? 4. So 4 times 2 is 8, and there's an 8. Then how many oxygens are required for this combustion process? So we have 3 times 2, 6 oxygens here. 4 times 1, 4 oxygens. So altogether, we have 10 oxygen atoms. And each molecule of oxygen has 2 oxygen atoms. So we need 5 molecules of oxygen to have 10 oxygen atoms. 5. Then how many nitrogen? Nitrogen is an inert gas, so it's not going to react. So 5 times 3.76 is the number of moles of nitrogen. That is 18.8. Was it difficult? Not at all, because this is the simplest case. We have a complete combustion. There's no carbon monoxide. There's no leftover hydrogen, oxygen, etc. So this is the simplest case. So it was kind of boring. So let's see if there is any more challenge. So this time we are going to add 20% more air. So this is going to be 120% theoretical air. So we are starting from this 100%, the standard balanced reaction equation. So this time we have 120%. So 5 times 1.2, that's what we need. So C3H8 is going to react with oxygen and nitrogen, but this time we are providing 120% theoretical air. So 5 times 1.2, so that's 6. However, it does not change the number of moles of carbon dioxide and water because the number of carbon atoms, number of hydrogen atoms did not change. So we still have 3 carbon dioxide and 4 water. Then how many oxygens do we need to have these reactions? 6 oxygen here, 4 oxygen here. All together, we need 10 oxygen atoms. And 6 times 2, we have 12 oxygens. So out of 12 oxygens, we only used 10 oxygens. So 2 oxygen atoms left over. So there's a 2 oxygen can create 1 molecule of oxygen. And we have nitrogen left over. How many? 6 times 3.76. 6 times 3.76, 22.56. So that's how we determine the balanced reaction equation. Again, whenever there is a combustion process, you need to be able to determine this balanced reaction equation because that's how you determine the total enthalpy of each component. Any question up to here? The last one is we have 120% theoretical air, but this time only 90% of the propane is consumed in the reaction. So let's see. So we have propane left over in the product. Okay. So the left-hand side is the same. We have a 120%, 6 times oxygen and 3.76 nitrogen. But this time, 10% of propane hasn't been consumed. So we have propane left over here. How many? 10%. So 0.1 moles of propane left over. Then we have a carbon here, so it's a complete combustion. So we have a carbon dioxide, we have a hydrogen here, so we have a water here, and we are providing more oxygen than it is necessary. So we have an oxygen here, and of course, nitrogen is going to be there always. So we need to determine the number of moles of carbon dioxide, water, oxygen, and nitrogen. So we have, let's talk about the carbon first. How many carbons? We have 3 carbons in the reactant, and we have 0.1 times 3. So 0.3 carbons in the propane, and then how many carbons required for this carbon dioxide? 3 minus 0.3, 2.7. So this one is 2.7. So 2.7 moles of carbon dioxide. What about water? Hydrogen. We have 8 hydrogens here, 8 times H. And we have here propane again, 0.1 times 8. 0.8 times hydrogen plus. Each water has 2 hydrogen atoms times 2 times H. So what's going to be in the box? 3.6. Now oxygen. we have 12 oxygen atoms in the reactant, and how many oxygens required for this carbon dioxide and water? We have 2.7 here. 2.7 times 2 oxygen plus, oh, there's a 3.6. 3.6 oxygen plus this one times 2 oxygen. So if you solve this equation, you can determine how many moles of oxygen required in the product. Where is it? 1.5. What about nitrogen? The number of moles of nitrogen does not change, because nitrogen is not going to react in this combustion process. So that's how you determine the balanced reaction equation for A, B, C. A, 2, 3, something wrong. A and B and C. Any question? If I give you, the problem like that, can you complete it? Yeah. So that's how we determine balanced reaction equation for a combustion process. Now, let's talk about how we can solve energy balance equation and entropy balance equation for this combustion process. So these are how we determine the mixture internal energy U, mixture enthalpy H, and mixture entropy S. So everything is on a molar basis. So we are going to determine the number of moles of each component. Let's say if it is oxygen and nitrogen mixture, the number of moles of oxygen times specific internal energy of oxygen plus the number of moles of nitrogen times specific internal energy of nitrogen. Okay? Pretty simple. The same thing here. If you want to determine the mixture enthalpy of this oxygen and nitrogen, the number of moles of oxygen times specific enthalpy of oxygen plus the number of moles of nitrogen times specific enthalpy of nitrogen. What about this mixture entropy? The same thing. The number of moles of oxygen times specific entropy of oxygen plus the number of moles of nitrogen times specific entropy of nitrogen. But there's one thing that you need to be careful, which is the pressure of the partial pressure of each component affects the entropy. So these are how we determine the specific entropy of each component. This is the equation you are going to use, which is actually the same as this equation using mole fraction, because the ratio between the mixture pressure and the partial pressure is the mole pressure. If you remember, mole fraction times the mixture pressure is the partial pressure. If the reference is only 1 atm, you can rewrite this one as this one. Okay, the same equation, it just depending on what is the reference pressure. We have a couple of practice problems, how to determine this specific entropy later. So you will see how to use this equation to determine the specific entropy from a table. So now the question is, how can we determine? So among them, now we know how to determine the number of moles, how to determine N of oxygen, N of nitrogen, N of oxygen, N of nitrogen, N of oxygen, N of nitrogen. How do we determine them? It's simple. If you remember the balanced reaction equation, these numbers represent N. So if you want to determine this N of nitrogen, this is N of nitrogen. This is N of oxygen, which is number 1. So whatever the numbers in front of each component in this balanced reaction equation is N. So now the question is, how do we determine this specific internal energy, specific enthalpy when there is combustion? So that's what we are going to study. How do we determine this H bar? How do we determine this U bar? But we are more focused on how to determine this H bar. Okay? So that's what we are going to study. To learn, to be able to determine H bar, we need to know another, the concept, which is the standard enthalpy of formation. Because, we have a combustion process. There's a reaction between two components and creating another component. So we need to know how much, the energy is related to that combustion. That is standard enthalpy of formation. That is H bar degree F. You can find this enthalpy of formation directly from a table, and this table is table A25. And if you go to table A25, we have the name of substances, their formula, their molecular weight M, and here you have their enthalpy of formation. And one interesting thing here is that the enthalpy of formation is 0 if you have carbon, hydrogen, nitrogen, and oxygen. Only those 4. So you can see when you have carbon, hydrogen, nitrogen, and oxygen, their enthalpies of formations are 0. What about other than these 4? Carbon monoxide, the enthalpy of formation is this number. Carbon dioxide, the enthalpy of formation is this number. Water, this number. There are 2 waters. One is gas phase, which is water vapor. The other water is liquid water. So this one is liquid water. You see L here. This one is water vapor. You see G here. So depending on the phase, we have a different enthalpy of formation. So then why there is a negative sign? What does it mean? When you burn carbon and it becomes carbon dioxide, this much heat is created and will be transferred from the reaction to the surroundings. That's why there's a negative sign. Okay, so this much heat is going to be created during the combustion from carbon to carbon dioxide, carbon to monoxide, hydrogen to H2O, hydrogen to H2O. At this condition, when the combustion takes place at 298 Kelvin and 1 atmospheric pressure, what if the temperature of this carbon dioxide, carbon monoxide, or whatever the products are at higher temperature than this? Of course, most combustion processes ending at higher temperature than this room temperature 298 Kelvin. Then there is an equation to determine the specific enthalpy when the temperature and pressures are different from these two values. That equation is written here. The specific enthalpy of a compound at a state where temperature is T and pressure is P can be determined by this equation. The specific enthalpy of, let's say, carbon dioxide can be determined by the enthalpy of formation of carbon dioxide. That's the enthalpy created by burning carbon completely. However, this number can be any value depending on the temperature of the product. So we use this standard number, enthalpy of formation, assuming that the temperature is the standard temperature. And we are going to use this correction to determine the exact specific enthalpy at the given temperature and pressure. So if you want to determine the mixture enthalpy H here, we need to know H bar of this component, H bar of this component. That H bar should be determined by this equation. The enthalpy of formation plus delta H bar. It looks complicated, but we have a problem together, so we will go over them, and you will see how we can determine this H bar. Okay? Any question up to here? So I guess I need to give you a brief summary of what we just discussed. Those it's a new concept, and you may get confused a little bit. So if you want to, let's say that we want to determine, we want to solve an energy balance equation such as Q in plus W in minus Q out minus W out. Let's say this is a constant pressure process. Then how do you determine the right-hand side? H2 minus H1. Right? That's how we determine the change of energy of a system. That is the simplest energy balance equation that we studied in Thermodynamics 1. Now, the problem is, how do we determine them? It's going to be the way we studied in Thermodynamics 1, in Thermo 1. How did we determine them? It was mass times specific enthalpy. So H2 minus mass times specific enthalpy, H1. And how did we determine this H? If it is a phase change material, then we use a table, property table, steam table, to determine this H. If it is a pure system, we use specific heat. So H2 minus H1 is CpT2 minus T1. So that's how we determined H2 minus H1. That's what we studied in Thermo 1. So if it is phase change material, then we use a table. If it is pure material, we use this specific heat. In thermodynamics 2, when we have a combustion, this H should be determined by this equation on a molar basis. The number of moles of one component, let's say carbon dioxide, times the specific enthalpy of carbon dioxide, but this is on a molar basis. That's why we add a bar on top of it, this one, to show per kilomole. Then how do we determine this H bar? We are using this equation. So that is N of carbon dioxide times the enthalpy of formation of carbon dioxide plus delta H. What is delta H? This enthalpy of formation is always at 25 degrees Celsius and 1 atmospheric pressure. But the carbon dioxide here at the final state can be at 100 degrees Celsius or 200 degrees Celsius or 300 degrees Celsius. We don't have a table for any different temperatures, only one temperature, 25 degrees Celsius. So if you have the carbon dioxide at, let's say, 100 degrees Celsius, then we are going to use this correction factor, delta H bar. Delta H bar. Then what is delta H bar? H bar at, let's say, 100 degrees Celsius. 100 degrees Celsius minus H bar at this temperature, 25 degrees Celsius. So we can add this term to determine the enthalpy at the given temperature, 100 degrees Celsius. So the final solution for this H is going to be N of carbon dioxide times H bar degree F plus H bar at the given temperature, whatever the temperature that you have, minus H bar at the standard temperature, 25 degrees Celsius. So this is how we determine this H. That's what we do in Thermodynamics 2 rather than Thermodynamics 1. Since we have 2H, we are going to use this equation to determine 1H. We are going to use this equation at different, of different material or different temperature to determine this H. So calculating H is going to take time, okay, in Thermodynamics 2. Why is that? Because we have a combustion. The governing equation did not change. We are using the same governing equation that we studied in Thermodynamics 1. We are going to use the same entropy balance equation that we studied in Thermodynamics 1. However, the difference between Thermo 1 and Thermo 2 is Thermo 1 is a very simple material, just oxygen, just nitrogen. But this time, carbon becomes carbon dioxide. Hydrogen becomes water. So we have a change of the substances. That is the reason why we use this complicated way to determine each component. There's no difference from the governing equation. We are just using different, more complicated way to evaluate each property because we have a complicated system. Okay? So by using this one, let's practice, the one simple problem, how to use this to determine enthalpy. We are going to calculate heating values of hydrocarbon fuels by using this one. Then what is heating value? If you have a gasoline, about this much, when you burn it completely, that means this gasoline consists of what? Iron Aluminum? No, it's a carbon hydrogen. So if you burn it, you will create carbon dioxide, carbon monoxide, water, right? So if you burn, let's say, 1 kilogram of gasoline, how much heat you can generate? That heat is heating value. When you burn something, how much energy we can get? When you burn coal in a power plant, how much heat we can get? So we can determine how much electricity we can, produce. If we burn, the gasoline, how much heat we can get so that we can run our car. So that is heating value. But there are two different heating values. One is lower heating value. The other one is higher heating value. Then why do we make, the two different heating values? Because we like things complicated? No, no, no. Problem is this one. The problem is this one, water. There are two different waters. Why there are two different waters? Water is just one, H2O, right? Of course, there's a heavy water, D2O. If you study nuclear engineering, we can talk about that when we have time. But the problem is that when we use this water, the maximum temperature is limited. So if you consider the thermodynamic efficiency, if you increase the maximum temperature, you can increase the energy conversion efficiency in a power plant, right? So which water has higher maximum temperature? Heavy water. So there are light water nuclear power plant, heavy water nuclear power plant. The difference is that light water is the water that we drink. Heavy water has one more neutron that will make it heavier, so that can withstand higher temperature. Of course, you don't want to drink it. I saw a YouTube video. Someone was actually drinking it. No, it's a small amount. It's toxic, but small amount is okay. But it was kind of, the shock to me, drinking heavy water. Just for some, the subscribers. And I saw that, yesterday. Clicked out. Okay, so we have two different waters because one is liquid water and the other one is, the water vapor. What is the difference? If you burn gasoline, sometimes the final product can be water vapor. Sometimes, the final product is going to be liquid water. And what is the difference? If the final product is liquid water, so more heat is removed from the reaction because water needs to be condensed down to become a liquid. That means that more heat is removed from the reaction. But if the final product is water vapor, then water vapor has more energy than liquid water, so less energy is released. So that's why there is lower heating value and higher heating value. Higher heating value means that we can create more heat because the final product is liquid water, and lower heating value means we produce less heat because the final product has water vapor. So that's why we have a higher heating value, lower heating value. The way to determine higher heating value and lower heating value depends on the water phase in the product. Okay? So if you go to table A25, you can see heating values. There are two of them, HHV, higher heating value, LHV, lower heating value. So you have different values, but the one thing you can see, for carbon, you have the same higher heating value, lower heating value. Why is that? Because carbon, there is no hydrogen, there is no water in the product. So there is no difference between lower heating value, higher heating value, because carbon has water, carbon has no hydrogen, so it cannot produce water. So let's see, if we can determine heating values of hydrocarbon fuels. What kind of fuel? Let's use liquid octane. What is liquid octane? If you go to table 825, there's octane. One is vapor. The other one is liquid. So we are going to use liquid octane to determine its heating value. What does it mean? Okay, so we have a liquid octane here. So I'm going to burn it completely. How much heat we can get? That is heating value. So let's do that. Then how can we determine, how much heat is released from this reaction? It's very simple. We can use the energy balance equation. What is the energy balance equation? Q in plus W in minus Q out minus W out, which is mass times H2 minus H1. That's the energy balance equation. Is that the only energy balance equation? No, this is okay. So we can let's use this equation. So this is the general energy balance equation. So we assume that by burning this liquid octane, we can produce heat. So that produced heat is going to be what? During this reaction, after this reaction, heat is created and it's going to be delivered to the outside, right? So this Q out is going to be the heating value. So heating value. By the way, are we going to determine higher heating value or lower heating value? The question is evaluate the lower heating value. That means that the water at the end is going to be water vapor, not liquid water. So we are going to determine lower heating value. And we assume that there is no energy transfer by work, there is no heat transfer into the reaction. Then this is the energy balance equation. We just need to determine the total enthalpy before the reaction and the total enthalpy after the reaction. So what is the system before the reaction? We have a liquid octane and we have air. After the reaction, we have carbon dioxide, water, and nitrogen. So we just need to determine H1 and H2. How can we do that? This H1 consists of what? Liquid octane, oxygen, nitrogen. What about this H2? There's no more liquid octane anymore because it's burned out. So we have a carbon dioxide, water, and nitrogen. So how many liquid octane, how many oxygen, how many nitrogen, and how many carbon dioxide, water, etc.? How do we know them? By using the balanced reaction equation. So the first thing we need to do is we need to determine the balanced reaction equation for liquid octane. So we are talking about liquid octane. Where's the liquid octane? So this is the balanced reaction equation. Liquid octane is C8H18. So let's determine the balanced reaction equation by ourselves first. So we have a liquid octane. It's going to react with what? Oxygen and nitrogen. Oxygen and nitrogen. Then if you assume that this is a complete combustion, what we can create? Carbon becomes carbon dioxide. Hydrogen becomes water. And what about nitrogen? Oh, it's not going to react, right? Then we need to know how many of each. So we can do that by completing this balanced reaction equation. How many carbons do we have? 8. C8H8? No, H18. My bad. Liquid octane. The chemical formula of liquid octane is C8H18. So we have 8 carbons can create how many? 8 carbon dioxide. And how many hydrogens? 18 hydrogen atoms can create 9 water molecules. So what about oxygen? By the way, the ratio between oxygen and nitrogen is going to be always 1 to 3.76. Then let's count oxygen. We have 8 times 2, 17. I'm sorry, 16 oxygen. 9 times 1, 9 oxygen. So we need 25 oxygens. So each oxygen molecule has 2 of them, 2 oxygen atoms. That means 12.5. 12.5 oxygen are required to have this reaction. Then what about nitrogen? 3.76 times 12.05. 12.5 is going to be 47. So this is the balanced reaction equation. Then what we need to determine first? H1. H1 is the total enthalpy of the reactant. So H1 is going to be H of liquid octane plus H of oxygen plus H of nitrogen. Then, how do you determine this H? This is how we determine H. The number of moles times specific enthalpy. The number of moles of liquid octane times specific enthalpy of liquid octane plus number of moles of oxygen times specific enthalpy of oxygen plus number of moles of nitrogen times specific enthalpy of nitrogen. That wasn't difficult, right? Now, what is this N? 1. What is this N? 12.5. What is this N? 3.76 times 12.5. 1, 12.5, 3.76 times 12.5, that is 47. 47. Then, how do we determine this H bar? How do we determine H bar? Oops, where is it? How do we determine H bar? By using this equation. H bar can be determined by the enthalpy of formation plus delta H bar. So this one can be determined by the enthalpy of formation plus delta H bar. How do we determine delta H bar? H bar at the given temperature minus H bar at the standard state, 25 degrees Celsius. What about this oxygen? H bar for oxygen can be determined by H bar degree F plus delta H bar at the given temperature minus H bar at the standard temperature, 25 degrees Celsius. This is the standard temperature. What about this one for nitrogen? H bar degree F plus delta H bar at the given temperature minus H bar at the standard temperature, 25 degrees Celsius. So how do we determine the enthalpy of formation? This one, table A25. Table A25. Do I have table A25? Where's my property table? Oh, right here. We can go to table A25. '24 and 25. So we need the enthalpy of formation of liquid octane, oxygen, nitrogen. Liquid octane, oxygen, and nitrogen. What is the enthalpy of formation? Oxygen, 0. Nitrogen, 0. Liquid octane, minus 249,910. So this number is the enthalpy of formation of a liquid octane, and 0 for nitrogen and oxygen. So this one is minus 249,910 kilojoule per kilomole. This one for oxygen, 0. This one for nitrogen, 0. Now, what is the temperature? Where was the problem? So here is the problem. What is the temperature of the reaction? 25 degrees Celsius. That is the same temperature of the standard state. So these two goes away and cancel them out. If the temperature is different from the standard temperature, you need to determine this H bar at the given temperature from another table, usually table A23. But this time, the temperature is at 25 degrees Celsius, so you can neglect them. Now, that's how you determine H1. What about H2? This time we have a carbon dioxide, water, and nitrogen. H of carbon dioxide plus H of water plus H of nitrogen. Then how can we determine this H for this carbon dioxide? The same thing, N of carbon dioxide, H bar of carbon dioxide. So this one can be determined by N of carbon dioxide times H bar of carbon dioxide plus water, N of water. But what kind of water? It's a lower heating value. If you want to determine higher heating value, liquid water, lower heating value, water vapor. So this one is vapor. Times H bar of water. plus N of nitrogen this time times H bar of nitrogen. Then how many moles of carbon dioxide, water, and nitrogen? Carbon dioxide 8, water 9, nitrogen 47. So this one is 8, this one is 9, this one is 47. Now, how can we determine H bar? The same equation, the enthalpy of formation plus delta H. So this one first. H bar degree F plus H bar at the given temperature minus the standard temperature, 25 degrees Celsius. This one too. H bar degree F plus H bar at the given temperature minus H bar at 25 degrees Celsius. What about nitrogen? H bar degree F plus H bar temperature minus H bar at the standard temperature, 25 degrees Celsius. Now, we need to determine the enthalpy of formation values from table A25. Carbon dioxide, water, nitrogen. Carbon dioxide, so this is the enthalpy of formation. Water, this time water vapor, so this number, and nitrogen, 0. So these three numbers. So for this carbon dioxide, we have minus 393,520 kilojoule per kilomole. For water vapor, minus 241,820 kilojoule per kilomole. And the enthalpy of formation of nitrogen, there's no enthalpy of formation of nitrogen. What is the temperature of the product? 25 degrees Celsius. So this one is the same as this one. This one is the same as this one. This one is the same as this one. So you can cancel them out. So that's how you determine H2 and H1. Once you determine them, you can put everything here, H2 minus H1, to determine Q out. If you do, so once you determine these two, we have everything, right? If you substitute everything back to this equation, you can determine Q dot out. So let me show you. Q out is going to be 5,074,630 kilojoule per kilomole. So that's how you determine the rate of heat transfer. But you may not like kilojoule per kilomole. From Thermodynamics 1, we are more familiar with kilojoule per kilogram. And how can you convert this one into kilojoule per kilogram? You can divide by molecular weight of liquid octane. What is the molecular weight of liquid octane? You can go back to table A25. There's a liquid octane, and the molecular weight is going to be 114.22. 114.22 kilogram per kilomole. So if you divide by this molecular weight, you get Q out to be 44,429 kilojoule per kilogram. So you can divide by molecular weight to determine mass basis, or multiply by molecular weight to determine molar basis. Then what is this 44,429? if you go to this table A25, the last column is lower heating value. That's what we just determined. For liquid octane, the lower heating value is 44,430, 44,429. So they are close enough. Yes. Molecular weight of this one, C8H18. So that is 114.22. Yes.
What did you say you could?
Okay, so if you want to get rid of this kilomole, divide by molecular weight. If you want to get rid of this kilogram, then multiply by molecular weight. So from here to here, divide by molecular weight. From here to there, multiply by molecular weight. Yes. Yes. Lower heating value means you create less amount of heat. Higher heating value means you create more amount of heat. When you create less amount, when you create higher amount, that depends on the phase of water in the product. When you burn liquid octane, you will create water, but if it is liquid water, that means liquid water has less amount of enthalpy than water vapor. So if you have a liquid water, that means more heat is removed, so higher heating value. When the final product has water vapor, that means less amount of heat is released. That's a lower heating value. So lower heating value means that you assume that the final product has water vapor. Higher heating value means that you have liquid water in the product. So when you have a combustion process and at the end, you see, the water dropping from the combustion product, that means that more heat is created. When you see water vapor, there's no, the condensate, meaning is that lower heat is created. So that depends on the condition at the exit of the combustion chamber. Okay? Yes. We assume that, that there is a water vapor in the product. That's why we determine lower heating value. If you assume that, that this H, water, is not vapor, but liquid, then you will use different specific enthalpy for liquid water. Then whatever you calculate is going to be higher heating value. So it just depends on, the phase of the water. So if you do not know the phase of the water in the product, you cannot determine lower heating value or higher heating value. So that condition, the phase of water, should be given. Yes. Then, if it is not 25 degrees Celsius, so this one is one of the easiest case because the reactant temperature is 25, the product temperature is 25. Is it possible? Not really. When you burn something, it's going to be pretty hot, right? So the product temperature usually very high, and the reactant temperature could be near 25 degrees Celsius. So if the temperature is greater than 25 degrees Celsius, which is most likely, which is going to be the problem that you will solve in your first exam, then there is a table A23. So you go to table A23 to determine H bar other than enthalpy of formation. So if you look at here, you have a H, the enthalpy of formation and just H bar. Just H bar can be found from this table, and the enthalpy of formation can be found from this table. Quite complicated. When it is quite complicated, it has a pros and cons. Of course, you need to practice a lot to get used to it. But the good thing is that since it is too complicated, I cannot make my problem more complicated. So it's going to be pretty straightforward. If you are able to, calculate this, then you should have no problem, solving the exams, because I know it is already complicated. I don't want to make it more complicated, right? So if you are able to solve this one, that's the bottom line, because the temperature is 25. So the next problem this one, this is the following problem. Now we have a simpler, the substance. Liquid octane is C8H18, but this time it's a propane, only C3H8. At the inlet, it is the standard temperature, 25 degrees Celsius. But at the exit, we have 560 Kelvin. So by solving this one, you will know how to use table A23 to determine the enthalpy, not at the standard temperature, but at elevated temperature. But we are out of time, so we will stop here. On Thursday, we are going to continue this, the problem. And I think we can finish chapter 13 this Thursday, because after this, we only need to apply another entropy balance equation, which is very similar to energy balance equation. So if we finish that this Thursday, your first exam is going to be the following Thursday after full break. Okay? We don't have next Tuesday. Oh, okay. So like, can we have an exam the following Tuesday so you can have, the nice full break? So everyone agrees, then we can do that. If there's anyone disagrees, then I can't do that, right? Oh, you can take them. No problem. Oh, you want them? This one? Okay. No, the rest I need. Oh,